Hey there, everyone. We're going to go ahead and get the webinar started here in just a few moments, but while people are coming in, I'd love to hear from you. Do go ahead and use the chat function at the bottom of your Zoom window and let us know if you've been to a Vernier webinar before. We'd love to hear from you. Well, if this is your first Vernier webinar, we are so thrilled to have you. Thank you so much for attending. Oh, and it looks like we do have a few first-time folks. That is so great. We are so excited to get into rotational magic with you. All right. As more folks trickle in, I do just want to do some light housekeeping, and then I'll pass you off to our presenter, Josh. In terms of that housekeeping, really, I just want to mention that we'll be sending a follow-up email with the recording of this webinar as soon as it's ready. We are kind of in the heavy conference part of our season, so we will be a little bit slower on getting that video out than we might be in other webinars, but do not worry, it is coming your way. You will get an email with the recording of that video, as well as all of the documents that were used today. You can get some free experiments, so that's coming your way. I'll make sure I drop a link to that folder in the chat today, so you also have access to that. We also are happy and excited to answer your questions. Please feel free to use the Q&A function, the chat function on Zoom. You can go ahead and drop any questions you have in there. Myself and Verl will be keeping an eye on the chat and answering your questions. If we happen to miss one of your questions, we'll definitely reach out to you privately and get that question answered. With that said, I'll go ahead and pass you off to Josh. Thank you all so much.
All right, thanks, Dylan. I'm going to start by sharing my screen here. And Dylan, will you put a link to this Google Drive folder in the chat there for everyone to see? Well, welcome everyone. Excited to talk to you a little bit about teaching torque and moment of inertia in your classes. This is a topic that I taught for several years, and I made a lot of mistakes. So I hope that you'll avoid the mistakes I make, and your students will learn this subject a lot better than mine did. We're gonna do a number of things today. I want to start off with a quick poll just to get to know you a little bit better. I'll introduce myself and my colleague Verl here who will be answering your questions in the chat. I want to talk a little bit about kind of teaching rotational motion, just an overview and some conceptual ways that you might choose to do that. But the bulk of the time I'm going to spend using this apparatus here, the centripetal force apparatus. And I want to talk specifically about three particular labs. The one that's called centripetal acceleration, another that's on rotational dynamics, and the last one on moment of inertia. Once we've kind of gone through those, there'll probably be some time for some questions at the end if you'd like. And then we'll kind of review how you'll get this recording later. So let's start with the poll. Simple 2-question poll. You'll see this pop up in front of you. I'm curious about, I assume you're a physics teacher, maybe amongst other things, but I'm curious, like what level of physics do you teach? And then also, how familiar are you with Vernier science education? So if you will pop those in there. Just by way of introduction, so my name is Josh. I have been at Vernier here for about 8.5 years. Prior to coming to Vernier, I was a high school physics and engineering teacher in Northern Virginia in Fairfax County Public Schools. I taught everything from conceptual physics to AP Physics C. I was also the faculty sponsor for our school's robotics team. Since coming here to Vernier, I do a lot of things. One of them is teacher trainings like this. Next week, I'll be in Atlanta for the National Science Teachers Association conference there, and I'll be doing more teacher trainings there in our workshop room. I help out with product development. A big part of my time is actually answering questions from our teachers. So if you ever have some piece of equipment's not working the way you expect it should, or you want to update your lab or something like that, and you call or email or chat with us on our website, I'm one of the folks that might answer those questions. There's a team of about 5 of us here that are all physics specialists, and Verl is one of them. He'll be answering those questions in the chat today that you have, and but we have others as well. So if you have questions, we want you to reach out. It's really we want to make sure, we know that this kind of equipment is expensive, and we want to make sure that you get the most out of it. It looks like, looking at the results of the poll, we've got a pretty experienced group here. 2/3 of the group is fairly experienced with Vernier. That's great, because I'm going to be talking about a lot of things here, and I imagine many of you, if you're especially new to it, you might have some questions about those details. You can post those in the chat, but it's great. We love our teachers. We like to think that we are a company made by teachers for teachers, and so we love you. Let's get into this. So I'm going to, I guess before we get into it, there's in that Google Drive folder, you'll find a copy of this presentation. You'll find copies of the labs that we're talking about in this particular webinar. There's also an extra one in there that's from our Physics Explorations and Projects book. That's an inquiry-based book, lab book, and but it's also around rotational motion, that sort of thing. I'm going to talk a little bit about the book called Ranking Tasks, and so I put a sample activity from that book in there, and then you also find a certificate of training that, you know, if you need it for that sort of thing, you can pass it on to administration as a proof that you were here. All right, so when it comes to that point in your curriculum that you have to teach rotational motion, maybe you're teaching AP Physics 1, and you get to that part of the curriculum, maybe it's AP Physics C. It's tempting to say, oh, well, we already know how to do this. You know, like all these relationships, we're already familiar with them. We're just swapping out, you know, X for theta, and we're swapping out V for omega. It's you just swap out these, you know, Latin letters for Greek letters, and you're good to go, right? Well, that's how I first taught it, and it's not as simple as that, unfortunately. Yes, the relationships are in many cases the same, but there's still a conceptual shift that your students have to make before they can really understand it well. My colleague Tom, who was also a physics specialist here at Vernier, he did a webinar, I think it was back in December, about teaching rotational dynamics and kinematics. There's a link to it in the presentation here. I encourage you, especially if you are looking for ideas, additional ideas on how to teach this subject, to watch that webinar as well. It's great. I kind of consider what we're going to do here today as kind of like a part 2 to that, to Tom's webinar there. When I taught, especially when I was teaching AP Physics C, those were pretty bright kids. You know, often, you know, usually it was their second year of physics. They were usually had taken AP Calculus or were taking it concurrently. So they were really strong students, math and science students. And at first it was really tempting. Like I said, I would just say, okay, well, you already know this stuff, you know, and I allotted a very short amount of time to really rotational motion. And I found that they struggled with it. And it's because we didn't spend the time together to really think about what the quantities meant before we jumped into the math. And so when it comes to teaching rotational motion, I think there are a few kind of experiences and sessions that you can have that help them start thinking about what theta means when you talk about, well, it's a rotation, you know, it's like it's our position, but it's a rotational angle. The first thing that we would do, I used very frequently in that AP Physics C course was these ranking tasks. Ranking tasks were really a book of activities put together by a pair of physics teachers years ago, and they're very conceptual. They present, you know, usually 6 or 7 variations of a situation, and they ask students to rank them in terms of things like, what's in each of these situations, which is rank these in or acceleration from slowest to greatest, or the sample one that I put in the folder there is all around torque, in which of these situations will the torque be the greatest, And I really like those activities because it didn't require a lot of math. They didn't have to pull out their calculators and start, calculating away. It was pretty easy for them to kind of get a sense for, okay, well, what do I need to do here? I usually would do this as one of those, think, pair, share activities where I'd ask students to rank, create a ranking themselves individually, and then talk to a partner about it. And if necessary, kind of update and revise their rankings. And then we would usually ask for a brave volunteer to share their ranking. And then we would have a discussion around, well, why did you do this? Those kinds of discussions were very helpful because they kind of help unearth a lot of the misconceptions or misconceptions that students might have about the particular topic that ranking test is on. So if you haven't ever heard of ranking tests, this is a great tool. They're fast, they're easy, and you can use them just in pretty much any sort of mechanics course. Another thing you might consider is using a turntable. One thing that I learned that actually the last few days was that in 2021, more vinyl records were sold than CDs. I thought that was impressive. Well, apparently we're making a comeback here. So if you have an old turntable, or even if you have a new turntable, they're great for just kind of talking about what does theta mean, what does omega mean, what does alpha mean, and how does that compare to, usually when you talk about linear motion, you might talk about a ball rolling down a ramp, or you might talk about a car accelerating from a red light, that sort of thing. And a turntable is a good kind of analogous situation there. And it's easy to kind of talk about what those quantities mean in the context of the particular turntable. Especially, I spent a lot of time at the beginning of my courses talking about how fast is a meter per second. We're going to do all of our calculations here in SI units. We're going to talk about speed a lot. How fast is 1 meter per second? And students would do activities walking to see how fast they walked or run and sprint and that sort of thing. With a turntable, you can take some easy measurements and say, okay, well, how fast is 1 radian per second? Is that a high angular velocity? Is it not? And then another thing that I found that was very helpful would be talk about rolling without slipping. I commute by bike. I have my entire professional career, and as a teacher, I usually have a bicycle sitting in my classroom because of that. And so we would talk about rolling without slipping. And the goal there was to connect the rotational motion of the wheel, or one of the wheels, to its linear motion as well. If it rolls through, 1 rotation, 2 pi radians, how far did it travel? Kids know that the circumference is 2 pi r, and they know all this math, but it's good to actually sit down and apply it to a situation in front of you, And that's that connection, that V equals R omega or delta X equals R delta theta sort of thing. Those are important because they kind of link our 2 worlds of motion here, linear motion and rotational motion. And then once they feel comfortable with that, then you can talk about slipping, and it's a little bit easier to kind of talk about when those 2 things get disconnected. So those are kind of the things I would typically talk about, conceptually, before we got into too much math and equations and the relationships. I'm going to change gears now for a little bit, and I'm going to talk a little bit about our centripetal force apparatus. I'm going to make this small and make this big so that we can see this. Okay, so this is our centripetal force apparatus. You'll see that it's really just like a rotating beam here with a couple of what we call carriages to hold masses. This sits on a real high quality bearing here, and kind of all the action is centered around this carriage right here, it's sliding, it's free to move up on a pair of bearings there. And because it's free to move like that, the only force, or I should say, the force that's causing it to move in circular motion is provided by the sensor here. This is our Go Direct force and acceleration sensor. It is kind of like our Go Direct sensors are all wireless, Bluetooth, or USB. It's kind of our updated force sensor. And so as this spins, the centripetal force pulling that mass, that carriage kind of into circular motion is provided by this force sensor, and it's easy to measure that. The Go Direct force and acceleration sensor has an added, has a couple extra sensors in there. There's a 3-axis accelerometer as well as a 3-axis gyro. And the z-axis of that gyro gives us a measure of the angular velocity of the sensor of the beam in radians per second. So this sensor alone will give us both the force and then a measure of the angular velocity as well. And in the graphical analysis software, we can collect both the data and then plot it against each other to kind of explore that centripetal force relationship. This other mass carriage here is fixed. It's kind of locked into place. Its role is primarily just to balance out the two sides. Likewise, the apparatus has leveling feet here so that you can balance it out. The apparatus comes with a series of extra masses that you can use to change the mat that is being added to each side. You can also adjust the distance, the radius at which your sliding mass moves. I have a couple of extra accessories attached to this right now. The first is a motor accessory kit. This is a motor mounted back here, and I can actually use this little rubber O-ring here to attach the motor to the bearing. There's a 3-step pulley kind of mounted to the bearing here, and then I can drive the beam at a constant speed. There are some investigations where that's really handy, and so that's a kind of an optional accessory there. The other piece that I want to talk about is maybe a little bit difficult on the video you see right now, but there is a pulley kind of mounted to the front edge of the centripetal force apparatus here, and that is part of the moment of inertia accessory kit. The moment of inertia accessory kit includes that bracket and pulley, as well as some pieces that you can use to swap out with the beam. So this is a metal hoop. There's also this is a plastic disc that you can mount horizontally, but then it also has a hole on the edge here so you can mount it vertically. This is a second plastic disc that's just nearly identical to the first. And you can use that so you can easily double the mass of the first disc. This is we have an activity where you look at the law of conservation of angular momentum, and you set one spinning and then you drop the second one on top of it to nearly instantaneously double its mass, and therefore look how that changes the angular velocity. So the centripetal force apparatus with the force and acceleration sensor, motor accessory kit, and the moment of inertia kit. It's makes for a great package to study all sorts of rotational motion and dynamics and rotational energy, all sorts of stuff there. As I mentioned before, I want to focus on these particular activities. The centripetal acceleration lab, rotational dynamics, and then moment of inertia. And I'm going to start with centripetal acceleration. This is kind of like the apparatus was kind of designed around this sort of experiment. And there are kind of two ways of doing it. You'll see that in the folder, in the Google Drive folder, there are 3 documents for this particular lab. There's the instructor notes, which is just what you'd think it would be. But then there are 2 versions of this lab. The first version, kind of the original version, was like what I call like a spin down method of collecting data. And the second version uses the motor accessory kit. I'm going to talk through the both versions a little bit for a minute here. So if I want to explore centripetal force, centripetal acceleration, I know that usually you're aiming for that relationship that the force, the centripetal force, is equal to the product of the mass and the velocity squared divided by the radius. And so with this apparatus, you can vary the mass by changing the amount in each carriage here. You can vary the radius by moving them in and out, and then you can also change the speed just by spinning it. And the fact is, this as this spins, there's a little bit of air resistance here. So you had set it spinning, and it's just going to naturally slow down. So if you record data over, say, 30 seconds, you're going to collect a variety of speeds, and you're going to collect force data at all those different speeds, and graphical analysis can display all that for you. So that's kind of that's the general idea of how it works. Let me show you how that data comes in in the app. So I'm going to first turn on my force and acceleration sensor, and then within graphical analysis here, I'm going to find it. Okay, so I'm looking for my force sensor. That's this guy. Connect to it. By default, it's going to collect force data, but I also want that angular velocity data, the z angular velocity. So that's going to be, I'm going to pop over the sensor channels here and find the z-axis gyro and add that as well. I'm going to hit done. So what I'm going to do here is I'm going to spin it up and then hit collect, and I'm just going to let it naturally slow down. I want it to slow down. I want to see a pretty big change in velocity. So I'm going to change my data collection rate, or I'm going to change, rather not the rate, but the duration. Rather than the default 5 seconds, I'm going to change it to, say, 30 seconds. And I can see here that my angular velocity in the lower right-hand corner here, I can see that my angular velocity is just about 0. That's what I expect. I'm going to zero out my force sensor. And I'm going to spin this up here and start collecting data. And it makes for kind of a boring graph here. Let's make these maybe a little bit better. You can see that the change in force is so small that it's not, it's not, see a lot of noise there. That's uncommon. But you can see my velocity is negative and it's becoming less negative. So it's slowing down. And likewise, the force is decreasing as well. That kind of makes sense that as it slows down, there's less force required to keep it moving in uniform circular motion there. And after 30 seconds, I've reached the end of my time here, and I had these two curves. Now we know that the force, you think about that relationship, we've got force on one side of the equation, and on the other side, you've got the product of mass and velocity squared divided by the radius. So I want to put these on the same axes. I'm going to make a couple of changes here before I do. First, I'm going to just go here to one graph. I'm gonna switch to just points rather than connected lines. And rather than plotting force versus time, I'm going to look at z angular velocity. So here I've got this kind of curve. It looks kind of linear. I'm going to, and it's really force versus the z angular velocity, which isn't quite what I want. If I want, usually you'll talk about tangential velocity rather than angular velocity, especially right at the beginning when you're talking about circular motion. I'm going to change this z angular velocity to just a regular linear velocity by going to my data table and creating a new calculated column. I'm going to make this a little bit bigger so you can see what's going on here. Here is my z angular velocity data. I'm going to click on this and choose to add a calculated column. And this calculated column is just going to be velocity. We measured in meters per second. And the expression, I'm just going to use a custom expression here. I know that to go from an angular velocity to a linear velocity, it's just r omega. You know, velocity is r omega. Right now, I believe, if I'm right, I have this set to just over 10 centimeters. So I'm going to choose 0.1 meters times, and then that z angular velocity. So it's going to create a column of data for me. And all it's going to do is take 0.1 and multiply by that z angular velocity. And it's going to say that's our velocity data. And I can see that just looking at eyeballing the graph there, or the data table, that looks right. And then on my graph, I can swap this out. Rather than plotting force versus the angular velocity, I'm going to plot force versus velocity. And not surprising, it looks just the same. And I want to ask myself, is this linear? It looks like it kind of, I mean, it looks like it might be. So I'm gonna do a curve fit here. And here's the linear curve fit. I can see it's not quite as good as I'd like. I can see, especially at the beginning here, I can see it's like the force is a little too great. Then the middle of my curve, it's a little too, I should say, the force is a little lower than the curve fit. And at the end, it's the opposite again. It's almost too great. That kind of leads me to believe that maybe this isn't linear, it's quadratic. So I'm going to go back. I'm going to try a quadratic fit here. And that looks really good. It's right, goes right down the middle there. The root mean square error is very, very small. And I have a number of the coefficients here, the fitting coefficients, correspond to my to some of the quantities here. We know that, you know, if we think of this y term, what shows up on the vertical axis is force, and this is velocity squared. We know that the constant a should be equal to the mass divided by the radius. And we could, you know, in the lab, students kind of verify that relationship there. You can also, depending on how you want to do this, that was a quadratic fit, but you can also, if you wanted, you could take and do another calculated column and plot out the square of the velocity. And that's pretty simple to do. My velocity, and I'm just going to square that y, and now I can plot. I've got a column of velocity squared, and I can apply it. I can plot there. Notice because I squared it, I also, all those negative values became positive. Now this now looks pretty good. That looks very linear. When I do a linear curve fit, I get an r value that's very close to 1. All right. So this is kind of like the way we originally wrote the Centripetal acceleration lab. Is you just let it slow down, and you collect a whole wide variety of forces and angular velocity data there. The only you know, as a teacher, the only problem with this lab is kind of getting to that relationship can be. I should say there are a number of distractions, right? Students are going to think to themselves, well, it's slowing down, so isn't my data affected by air resistance? You know, and that's, you know, it takes a little bit of thought to think, well, yeah, I guess it's, you know, the centripetal force isn't necessarily affected by that aerodynamic drag, you know, but it kind of takes a little bit of thought to kind of, how does that work, you know? So there's Verl wrote a version of this lab, an alternate version of this lab. Rather than just letting it spin down, it takes advantage of the motor accessory kit. So that second version of the lab, rather than just spinning it up and then letting it slow down, you attach the motor accessory, the motor to the beam, and you drive it at different speeds. And in that case, it's really more of what is the centripetal force at this given speed, and then you change the speed Now what's the new centripetal force at this next speed? And then you change it again when you do a number of data points there from slower speeds to higher speeds. And you kind of create this same sort of graph, just piece by piece, and while that's a little bit slower, conceptually, it might be a little bit easier for your students to kind of get their head around, like, what are we doing here? And how does you're very clearly thinking that the speed that you're choosing as the independent variable, and that centripetal force that the probe is measuring as your dependent variable. So that's kind of an alternate version to that. I kind of like that version, just because, especially when I think about those first year physics students, that can be a little bit easier. There's a little less distraction around what the relationship is that you're measuring there. All right, let's talk a little bit about the second lab.
And we had just a few questions in the chat.
Perfect.
Perfect. Rebecca was just wondering, do you use the sensor for uniform circular motion?
You can, yes. This especially when you drive it with the motor accessory kit, you're really getting uniform circular motion there, and so it works real well for that. When I taught uniform circular motion, you might have an apparatus where you could attach a force sensor kind of to a stopper on a string. You swing it around your head, you get hit in the head a lot, but you'd swing this thing around your head, and you had the string hooked up to a force sensor. You measure the force, and then usually you had a stopwatch that you're using to measure the rotational rate. You can do that sort of lab with this particular probe, but this thing will measure the angular velocity for you, so that's kind of nice. You don't have to use the stopwatch.
And then one more, does the fit y equals mx plus b show uncertainties in m and b?
Let me think. I'm pretty sure you can add those. Yeah. So this is a relatively new feature added to Graphical Analysis Pro. Maybe I'll make this a little bit bigger so you can see what happened there. So this little helper box that shows the linear fit, the fitting parameters. Now you can see there is an uncertainty applied to both M and B. The way that's found is by this little gear icon. You can kind of check or uncheck this box here. And that, like I said, that's a relatively new feature. Graphical Analysis is kind of like our latest data collection app. It is like Logger Pro in the sense where it connects to our interfaces and our sensors. You collect data into it, and it's got all these options to do curve fits and statistics and that sort of thing. It's our cross platform app. So I'm on a PC right now, but you can get the same app. And it looks and feels just the same on a Chromebook as it does on a Mac, as it does on an iPad. It's touch friendly, that's why. So it looks much different than Logger Pro does. And you can just download Graphical Analysis for free. And with that free version, you can do about 90% of what Logger Pro can do. You can also purchase a license for Graphical Analysis Pro, which includes a lot of the more advanced analysis options, like, for instance, the uncertainties on these curve fits. Other things like there's some advanced analysis procedure. Oh, I guess when I did the calculated columns before, I just inserted a custom expression. That's a pro feature. Otherwise, you use just the standard equation types that they have listed there. There are a number of remote learning options that allow you to stream data over the internet or sync video data to data collection and that sort of thing. So yeah, you can do the uncertainties. You can find those uncertainties, but you do have to have the pro license for that. All right, let's talk a little bit about rotational dynamics. The second lab. This second lab is you want to talk. This is for the second lab. The relationship that you're really investigating is Newton's second law for rotational motion. So torque, the sum net torque, is equal to the product of the moment of inertia and the angular acceleration. And the way that the format for this lab is is very similar. You know, you've got the force and acceleration sensor up here. You're going to be spinning this beam, but instead of spinning it with your hands, you're going to apply a torque to the apparatus using a hanging mass. You know, so like I've got a hanging mass here and a string. It might be a little, maybe I'll turn this for a sec here. This, you can kind of see there's this pulley mounted out front here. This is like a lab bench behind me. And you apply that torque to the pulley, or I should say, you apply a torque to the bearing using the 3-step pulley here. That's the idea, is that, you know, as it falls, it spins the apparatus. There are a couple of things you can investigate there. Obviously, you can change the location of the mass carts of the carriages here. So that's changing I. You can also change the radius at which the torque is applied. You know, the R, you know, as torque is R across F. There's the 3-step pulley here. Each is a different, you know, obviously a different diameter. And the pulley out front here can slide side to side and up and down, so you can always get it so that it's, you know, it's the string is kind of perpendicular, tangential to the 3-step pulley on the bearing here. This lab, this rotational dynamics lab, you have the students, you know, they collect a number of runs a day. They vary the amount of mass, so the force, the falling weight here, and look at how does the angular acceleration change as you change that the falling mass. In this case, you're only using the force and acceleration sensor to measure that angular velocity, and you're looking at that angular velocity and you're seeing it increase, and you're taking the slope of that to find the angular acceleration. This lab is very similar to the moment of inertia lab that's also in the folder there. The main difference is, rather than I mean, what you're doing there is you're dropping these masses and looking at the angular acceleration. The difference is, rather than kind of trying to get at that, you know, sum of torques is I times alpha relationship, you're looking particularly at I. It's like in the moment of inertia lab, you take for granted that the students already know that Newton's second law relationship, and instead you're focusing on how does the moment of inertia for this beam compare to the moment of inertia for this disc, compared to or this hoop versus this disc, and so on and so forth. I'm going to set that up real quick here, and the way that works is I'm going to take off this beam here. It just kind of, there's just a screw here that kind of tightens it down on the axle, and I'm going to use another force and acceleration sensor here, and it just slides onto the same axle that the beam is on. At this point, remember, I'm only going to use this for that z-axis angular velocity, so I don't really need to worry about what the force sensor is doing there. And then I'm going to add on here I'm just going to use this hoop here. It's a metal hoop. I guess one thing I'll note here is this guy can be mounted horizontally or vertically. If it's mounted horizontally, it's got this groove in here so that the metal hoop mounts on that or sits in there pretty easily. Both the disc and the hoop are just about the same mass, you know, so it's kind of, you add that and you kind of effectively double the mass. I'm going to mount this guy though in a vertical orientation like this. And actually, I'm gonna do one more thing. I'm gonna mount this. There are lots of different ways you can attach string to these pulleys, and when you're doing it in front of an audience, this might be the easiest way. All right, so I'm gonna go. All right. And this guy over here. And now I'm going to go to graphical analysis. So I'm just going to go to a new experiment here. This data is nice, but not enough to save. And I'm going to switch the force and acceleration sensor that I'm using. We are G5. In this case, I only want the z-axis gyro. The force sensor isn't connected to anything. All I'm looking for is this rotational speed. So I've got one graph here. And the way this is going to work is I'm going to wind this guy up. And then I'm going to let that mass fall. And I'm going to look at the rotational acceleration from that graph. This string is about a millimeter wide, which is about as pretty good for this particular, like this pulley and this three-step pulley that's mounted to the bearing here. That's kind of like the sweet spot is about a millimeter. That's wide enough that it sits nicely in this pulley out, the super pulley out front. And it's also big enough that there's a notch in this pulley that you can kind of attach to. That notch is about a millimeter wide, so it fits in there as well. All right, so I'm all wound up here. I'm going to hit collect, and then I'm going to let it drop. So collect here. Yeah, this guy. All right. So looking at my graph, I know that during this portion of the graph, this is when it was speeding up. You know, when it was starting to spin up. And so if I do a curve fit on that portion of the graph, I'll get the angular acceleration, alpha, from that. You know, this is a graph of omega, and the slope of that is going to be my angular acceleration. So right now I can see that that angular acceleration was about 10.77 radians per second. And in this, in the moment of inertia lab, you would then take and swap it out. You'd take this off and you'd add just this disc. You know, you might compare it to vertical versus a horizontal orientation. And you might double that. So it's the same orientation, but you're going to double the mass of that particular one. That lab also compares to just the beam. Obviously, you would take off the sensor, just the beam, and you would just look at that beam, that sort of thing. That moment of inertia lab is neat because you're really taking real moment of inertia data, or you're looking at this acceleration, and you can compare it, and then you can compare it to what's in the textbook. You know, what's the moment of inertia for a hoop of this mass and this diameter rotating about, its diameter like that. You'll find, especially if you look at the teacher notes, the instructor notes for that moment of inertia lab, you'll find that there's not a small percent difference between what you would theoretically get and what you actually get. And that opens the door to all sorts of questions and investigations. One of the things that's provided in the teacher notes is an approximate moment of inertia for the axle itself. One thing that's interesting, especially if you get, depending on how fast you get these guys going and stuff, you'll find that this particular disc, when it's mounted vertically, when it spins vertically, there's a significant amount of, or I should say a noticeable amount of air resistance, and that plays into it. So it's definitely, it moves from the theoretical to the real world very quickly, but there's lots of rich investigations you can do there. Yeah, so I encourage you to look through those labs and think about them. Let me go back here. What questions do you have at this point?
Looks like we're good to go so far.
All right. Well, I appreciate your time. Appreciate having this opportunity to talk to you a little bit about rotational motion. It's a great topic. It's an interesting one, a really rich one. And I hope that as you get into the lab with your students there and you start thinking about these sorts of things, that you also think about us. if you have any of these probes or equipment and you have questions about them, or you want a little bit more one-on-one time, please reach out. We do kind of Zoom trainings all the time in a one-on-one sort of format. And they're really a great way for us to meet you where you're at and to kind of talk through these sorts of situations. As Dylan mentioned earlier, there is, we'll package up this webinar and you'll get an email with a link to the recording so that you can view it later.
All right. Thanks, everyone.
Thank you,
It
everyone.
looks like we have a few questions, actually. First, from Joel, the angular velocity sensor is the blue thing in the bottom
I
with
see.
the bearing?
No, the angular velocity sensor is actually, that gyro is in this sensor right here. The bearing down below is just a bearing. That's all it is. So it's got that 3-axis gyro built into the sensor. That's where we're getting that angular velocity. Yeah, I guess I'm looking at your question there as well, Joel. This particular force sensor, it is a force sensor. It has a load cell in it. In this case, we're not using it because it also has a 3-axis accelerometer and a 3-axis gyro. You know, and that gyro measurement gives us that angular velocity, and that's what we're measuring there. Daniel, you want to see what's creating what's keeping this pulley stationary? I'm going to share my screen again so I can use that better camera there. And I'm going to go over here and I'm going to make this bigger. So I had leveled this carefully before, but I feel a little bit more free to move around now. So you'll see that there's this bracket here that attaches the super pulley to the base of the centripetal force apparatus. I'll take this out here so we can show it a little bit closer. It just screws into the bottom, the base here. You can kind of see that it's just a bracket. And the size of this thing is just right so that when it's mounted here, it lines up well with the bearing. And you can actually, maybe I can get this so you can see it a little bit better. The slot here where you attach the pulley is actually it's on a diagonal so that you can line it up real well with the 3 steps of the pulley here. So it's always, you know, you don't have it's not diagonal. The string isn't diagonal at all when it's pulling on the pulley. Yeah. I noticed that before when I was setting this up, that the camera was just so straight on that it was kind of hard to see that there was even a pulley there, you know.
It looks like Gail is wondering how this experiment can be done with older sensors and potentially non-wireless sensors.
Yeah, so Gail, one of the things that this guy's really nice for, because it's got a lot of versatility to it. I actually grabbed, before I came here today, you might have our rotary motion sensor. This is the wired version, but there's the wireless version, the GoDirect version, but there's also a wireless version, you know, or I just said the same word. There's also a wired version, and it's just the rotary motion sensor. It's like order code RMV-BTB. But this is the same sort of thing. In this case, the rotary motion sensor would be measuring your angular velocity for you. And this is this rod here with these masses and the pulley and stuff are all part of an accessory kit, the rotary motion accessory kit. And you can, this centripetal, no, the torque one, which one was that called? The rotational dynamics lab was originally written for this particular probe with this accessory kit, you know, so it's the same sort of idea as you kind of hang this, you got the pulley kind of hanging over the edge of the table and you hang a mass off of it so that it turns the rotary motion sensor, the beam, as it does. This obviously you've got these pieces, which is just this rod with these masses that you can kind of move in and out to change the moment of inertia. And then the accessory kit also comes with a couple of discs that you can mount on there as well. So that's kind of where it works. I should say that's kind of, those are the options there. There isn't a corresponding disc that could be mounted vertically. That you have to have the big guy for that. Do you need any extra equipment no, you don't. So if you have the rotary motion sensor and the rotary motion sensor accessory kit, you can do that conservation of angular momentum lab with these pieces. The flip side to that is if you have the centripetal force apparatus with the moment of inertia accessory kit, you can also do that same lab. It's just that you would use these big discs with that instead of the little ones on the rotary motion sensor. As far as whether it can be done manually, I guess you probably could if you're really good with a stopwatch. The way that you would do it manually is you'd want to be able to, you would need something that spins really well, like a nice bearing, and you'd use like a pair of discs like these. And what you'd want is, let me see how focused that is. You'd want to put a dot on there, and you'd set it spinning. And you would use a stopwatch to measure how long does it take to go around 10 times, and that's your initial angular velocity. And then you would drop your second disc on top of it. These have a hole in them, so it's easy for them to align them. The little axle goes through both of them, so it's easy to do. But you'd want another spot on this one, and then you would do it again. You would record how long did it take for it to go 10 rotations as well. And you'd use that as your angular velocity afterwards. It'd be a little tricky to pull off really well. The problem is it would be easiest to measure something like 10 rotations with a stopwatch, but it's likely that they slow down just by friction significantly over 10 rotations. And so it's kind of like the angular velocity that you measure before and the angular velocity that you measure afterwards they might not always line up. They're kind of like an average velocity before and an average velocity afterwards, and how well that shows that conservation of angular momentum relationship, it might not be really good. You'd want to play with it. And the right combination of discs and bearings and stuff like that is obviously going to make a difference. These are great questions, folks. And I love discussing them. If we once we go part ways here, and tomorrow you're thinking about this webinar, and you're like, well, what about that? Please call, email, come chat. I love to answer these sorts of questions. What's the total cost for one set of the apparatus using today? So I don't know. I have to look on the website. I think the force sensor itself, so the that does the measuring, it's, I think, $110 or something like that. And then the apparatus itself is another $299, I think, maybe. I don't know. Oh, thanks, Burl. Burl's got my back. $325 for the centripetal force apparatus. And then there's the force and acceleration sensor on top of that. And then there's the accessory kit for the motor accessory kit, and the moment of inertia accessory kit are all separate purchases as well. And those are kind of like, it depends on how you want to do it. If you just to get started with what we had here, the force and acceleration sensor and the centripetal force apparatus are kind of like the core of it, and it looks like it's $119 for the force and acceleration sensor and $325 for the centripetal force apparatus. All right, yeah. Lewis asks, do these not work with Logger Pro? That is true. So the newer generation of probes, the Go Direct probes, they do not work with Logger Pro. They do work with the graphical analysis type. Obviously, that's what you've seen here. But Logger Pro is 23 years old at this point, and shoehorning in yet another feature would require kind of rebuilding the whole thing altogether. So Graphical Analysis Pro is kind of like, it's our path forward. We still support Logger Pro, and it works great for the older generations of those LabQuest sensors and those older wired sensors. And if you're using them now, you can still get tons of great service out of them. You might try, if you haven't, you should try Graphical Analysis. It'll work with LabQuests and LabQuest minis and that sort of thing, and it works on a Chromebook, which is kind of nice. And yeah. Gail asks, is Logger Pro going to become obsolete? I imagine at some point Microsoft or Apple is going to make some change to Windows or Mac OS that kills Logger Pro. Right now, Logger Pro requires a lot of effort to keep it up and running on these newer modern operating systems. You have to remember it was designed back in the not Windows, before Windows XP age, so it takes a lot of work just to keep it up and going. And it's likely that there will be some day when Microsoft makes a change to Windows that it's going to cost way more to rewrite Logger Pro to run on Windows than it's worth it to our developers. And so at that point, it'll be you either have to not update Windows or you have to switch to Graphical Analysis. Carlos, I hear you. Logger Pro, it's got a special place in my heart too. Yeah, Burl makes a good point there that you can export data from Graphical Analysis into Logger Pro to get there are some of those features that aren't in Graphical Analysis yet, and you can always export it into Logger Pro and then use those features there. Graphical Analysis licenses are not really. You buy a license for a couple of years. You can buy it 1 year at a time. There are 3-year licenses available. I don't know if they're on the website, but you can also buy 5-year and longer licenses. But you might have to ask special for those. Does Graphical Analysis have video analysis in it? It does not. Graphical Analysis is only for like sensor data collection and manual data entry. There is a separate app called Vernier Video Analysis, which looks a lot like Graphical Analysis, but has the video features built into it. It's actually a slightly different beast because it runs within a browser, so there's nothing to install there. And that means it runs just the same on an iPad as it does on a computer, It uses the same sort of analysis features and graphing features that Graphical Analysis Pro does, but it is a separate license and a separate app. In fact, I can, I'll share my screen here real quick because there is one of the sample videos in video analysis is a turntable of all things. Yeah, so this is Vernier Video Analysis. I'm in the Chrome browser right now, and it's just running within my Chrome browser. And if I choose this turntable sample video, this is just a turntable, and I can just like the video features in Logger Pro, I can add points to this. I can choose. I can set a scaling length. I can choose an origin and that sort of thing. The data that I collect end up over here in my data table and my graph. And then I've got all sorts of the same sorts of analysis features that I did in Graphical Analysis Pro. Yeah. So there's that. There's a question. Can we use older force and motion sensors with newer software? Louis, likely you can. The biggest, the biggest, the way you would connect those older force and motion sensors to the computer and Graphical Analysis would be with an interface like a LabQuest Mini or something like that. Any of the LabQuest generation interfaces or like a GoLink, that'll work. The older Lab Pros, those will not work with Graphical Analysis. Those were, we stopped making those back in, I think, 2009 or something like that. So they're durable. There are still a lot of them kicking around out there.
All right, I think we are bumping up on time, so.
All right. Well, again, thank you all. I love these kinds of conversations. They're fun to have. So please, if you've got questions, reach out. We'll be reaching out in a week or two here with a recording of this webinar. And if you've got questions, then just reply to that email and send it our way. We're happy to help.
All right. Thanks, everyone. Bye now.
Bye.